Hello everyone, welcome to Probability Models course. This course teaches the math behind machine learning, network queues, Markov models, and Monte Carlo methods. Today we review probability theory. I know you have seen this before, but we need everyone to start at the same level. Okay, this course has 8 parts. Part 1 is probability basics. That we are going to cover this topic today. Part 2 is random variables and common distributions. Part 3 is statistical inference like MLE, MAP, Bayesian estimation, and other methods. Part 5 is queuing models like packets coming to a router. Part 6 is the EM algorithm. Part 7 is graphical models. Part 8 is Monte Carlo methods like MCMC, Gibbs sampling, Metropolis Hastings, and some other methods. Every part connects to real computer science problems. Well, today we cover 8 topics. 1. Foundations. 2. Conditional probability and independence. 3. Total probability theorem and Bayes rule. 4. Random variables. 5. Common discrete distributions with some examples. 6. Common continuous distributions also with some examples. 7. Multivariate Gaussian distribution. And at the end, we are going to cover some exercises and discussion on this session. I should mention that multivariate Gaussian distribution is very important for machine learning. So let's see what is probability. Probability measures uncertainty and is a number from 0 to 1. In this topic, we need 3 basic ideas. First is all possible results. We call this omega or sample space. For example, if you roll a dice, omega will be 1, 2, 3, 4, 5, and 6. For another example, if I measure how long a server lives, omega or sample space is all positive numbers. Second one is something that can happen, and we call it event or E. For example, the dice shows an even number. That means 2, 4, or 6. This is an event. Third, a rule that gives a number between 0 and 1 to each event. We can give a number between 0 and 1 to each event, and that is the probability of that event. Also, we call this P. There are 2 ways to think about probability. The frequentist view says probability is what happens in the long run. For example, if I flip a coin many times, the fraction of heads approaches 1/2. On the other hand, the Bayesian view says probability is a degree of belief. If I say there is a 70% chance of rain tomorrow, I'm saying how strongly I believe it will rain tomorrow. Both views give the same math. To conclude, probability provides the mathematical language for reasoning under uncertainty, and this measure is essential for machine learning, robotics, and network design. In 1933, Andrei Kolmogorov wrote 3 simple rules or 3 axioms. All of probability comes from these 3 rules that you can see here. Rule 1, probabilities are never negative. P of E is always greater than or equal to 0. Rule 2, the probability of everything together is 1. Or in other words, probability of sample space is always 1. Or P of omega equals 1. Rule 3, if two things cannot happen at the same time, then the probability that one of them happens equals the sum of their probabilities. This is axiom 3 or rule 3. For example, if A and B cannot both happen, then P of A or B equals P of A plus P of B. From these three rules or axioms, we can prove useful facts that you can see here. Fact 1, the probability of nothing is 0. This means nothing happening. Again, probability of nothing happening is always 0. Why? You may ask why. Because omega equals nothing union omega and they do not overlap. So P of omega equals P of nothing plus P of omega. Subtract P of omega from both sides. P of nothing equals 0. Fact 2, P of not E equals 1 minus P of E. This means not E, P of not E is 1 minus P of E. Fact 3, P of A or B equals P of A plus P of B minus P of A and B. This is P of A and B. This means A and B happening at the same time. The minus part, this part, fixes a double counting of P of A and B. To conclude, everything in probability theory derives from these three axioms. These three axioms are very important in probability theory. Okay, conditional probability. Conditional probability is how we update our beliefs when we learn new information. When new information comes, our belief may change. Its formula is shown here. The formula is P of A given B equals P of A and B divided by P of B. We need P of B greater than 0. P of B always should be greater than 0 because we cannot have 0 at this place. Or in other words, we cannot condition on something impossible. Probability of something is 0. This means that that thing or that event is impossible. Let's see what does this mean. Imagine we learn that B happened. Our world shrinks from all of omega to just B. Now we may ask within B how much is also A. This is probability A given B. From this formula, we get the product rule. This is the product rule. P of A and B equals P of A given B times P of B. This also works for three events. P of A and P of A1 and A2 and A3 equals P of A1 times P of A2 given A1 times P of A3 given A1 and A2. This is the basis of Bayesian networks that we will see this later. This is the extension of this product rule to n events that you can see here. Okay, let's do a simple example. Roll a fair dice. Let A B outcome is even. That means A should be 2, 4, and 6, and B is outcome greater than 3. This means that B should be 4, 5, and 6. Our sample space is 1, 2, 3, 4, 5, 6, all possible numbers when you roll a dice. The problem asks us to find P of A given B. According to the formula of P of A given B, we should first find P of A and B. A and B are 4 and 6. This means that 4 and 6 happen at the same time in A and B. A and B, so should be 4 and 6. Okay, let's find P of B. P of B will be the number of figures in B, that is 3, divided by the number of sample space, that is 6. This equals 1 divided 2. The probability of A and B would be the number of figures in A and B, that is 2, divided by the number of figures in the sample space, that is 6, and this results in 1 divided by 3. According to the formula of P of A given B, we should divide P of A and B by P of B. 1 divided by 3 divided by 1 divided by 2, that results in 2 divided by 3. Let's see if this makes sense. We know the result is in 4, 5, and 6 because our sample space shrinks to B. Two of these three numbers are even, 4 and 6, so the answer should be 2 out of 3. 2 out of 3, our new sample space, that is our final probability that we find based on the formula. So we can see that the math matches our intuition. Okay, now let's talk about independence. Two events are independent if knowing one does not change your belief about the other. Mathematically, A and B are independent if P of B and P of A and B equals P of A times P of B. Another way to say it, if P of B is greater than 0, then P of A given B equals P of A. These formula about independence are equal. Well, let's explain about it. Learning B happened does not change the probability of A, or we know that B, if B happens, the probability of A does not change. Therefore, P of A and B should be P of A because happening B does not change the probability of happening A. This means that A and B are independent. Or in other words, if you put the formula of P of A given B here, you can come to this formula that says P of A and B equals P of A times P of B. Here you should be careful because pairwise independence is not the same as mutual independence. Pairwise means every pair is independent. On the other hand, mutual means every group is independent. Let's have a famous example. Imagine a tetrahedron with 4 faces. One face is red, one face is blue, one face is green. The fourth face has all 3 colors. Let A be the bottom face shows red. Event A, so is the bottom face shows red. Let B, event B, be the bottom face shows blue, and let C be the bottom face shows green. Each pair is independent. For example, P of A and B equals 1/4, and P of A is 1/2, P of B is 1/2, so 1/2 times 1/2 equals 1/4. Okay, But all three together are not independent. P of A and B and C equals 1/4. But P of A times P of B times P of C equals 1/8. They are not equal. 1/8 is not equal to 1/4. So pairwise independence does not mean mutual independence. Okay, let's talk about a law of total probability. The law of total probability is a trick for breaking hard problems into smaller, easier pieces. First, we need a partition. A partition splits omega into groups that do not overlap and together cover everything. For example, think of cutting a pie into slices. No slice overlaps another, and together they make the whole pie. The law of total probability says P of A equals the sum over all groups Bi of P of A given Bi times P of Bi. This is the law of total probability. Let's see why this is useful. Sometimes P of A is hard to compute directly, but if we condition it on some extra information like Bi, then P of A given Bi becomes easier. We compute the probability in each case, weight it by how likely that case is, and then add them up. This law is also the key to making Bayes' theorem practical. Bayes' theorem is an important theorem that we will talk about it later. Without this law, the bottom part of Bayes' formula would be impossible to compute, and we will cover it in some later slides. This figure relates to an example that I'm going to talk about it in the next slide. Okay, let's have an example. A factory has three machines. M1 produces 50% of items with 2% defect rate. M2 produces 30% with 3% defect rate, and N3 produces 20% with 4% defect rate. What is the overall probability of a defective item? We want to know in what probability an item would be defective. In other words, pick one random item from the factory. We want to know what is the probability that it is defective. We don't know which machine made this item, so we cannot just say 2% or, for example, 3%. To find it, we should use total probability. In this regard, P of defective, P of becoming an item defective equals P of D given M1 times P of M1 plus P of D given M2 times P of M2 plus P of D given N3 times P of N3. That is 0.02 times 0.5, 0 plus 0.03 times 0.3, 0 plus 0.04 times 0.20, which equals 0.027. Therefore, the overall defect rate is 2.7%. You should notice that this is a weighted average. This is a weighted average. M1 makes the most items, so it pulls the average toward its 2% rate. M1 produces 50% of items. Therefore, when we average based on the ratio of products that each machine produces, M1 pulls the average toward its defect rate, that is 2%. Bayes theorem. Bayes theorem is probably the most important formula in statistical machine learning. This formula tells us how to flip conditional probabilities. The formula is P of Bi given A equals P of A given Bi times P of Bi divided by P of A. So let's read each part separately. P of Bi given A, this one, P of Bi given A is the posterior. It is our updated belief about Bi after we see A. P of A given Bi is the likelihood. It tells us how likely the data A is if Bi is true. P of Bi is prior. It is what we believed about Bi before seeing any data. And P of A is the evidence. We compute it using total probability that we talked about it in the previous slides. Therefore, P of A equals the sum over J of Pia given Bj times P of Bj. So the full formula is P of Bi given A equals P of A given Bi times P of Bi divided by the sum over J of P of A given Bj times P of Bj. Pa is replaced here. A shorter way to remember for you, posterior is proportional to likelihood times prior. In machine learning, the prior is our belief about model parameters before seeing data. The likelihood is how probable the data is for different parameters, and the posterior tells us what we should believe after we see the data. Bayes theorem is the cornerstone of Bayesian inference, spam filters, medical diagnosis, and different machine learning classifiers. And it's, as I said, it's probably the most important theorem and formula in statistical machine learning. Okay, let's have an example. This is the famous medical testing problem. It shows something very surprising. A disease affects 1% of the population. The test is 99% accurate. If you have the disease, the test is positive 99% of the time. And if you don't have the disease, the test is negative 99% of the time. You take the test, it is positive. What is the probability you actually have the disease? Okay, most people guess about 99%. The test is 99% accurate, right? Let us do the math. Let D be you have the disease, and let T plus be the test is positive. We want P of D given T plus. We want P of D given T plus. Bayes theorem says P of D given T plus equals P of T plus given D times P of D divided by P of T plus. This is the Bayes theorem formula. The numerator is easy. P of T plus given D equals 0.99. P of D, this part, equals 0.01. Numerator therefore equals 0.0099. that is 0.99 times 0.01. On the other hand, the denominator p of t plus has two parts. We have added two parts of p of t plus. Part 1, true positives. People who have the disease and test is positive. P of t plus given d times P of d equals 0.99 times 0.01. That is equals 0.0099. And part 2, false positives. This part, people who don't have the disease but test is positive. P of t plus given not d times P of not d equals 0.01 times 0.99, and this equals 0.0099. Total P of t plus equals 0.0099 plus 0.0099 equals 0.0198. Now we should divide 0.0099 divided by 0.0198 equals 0.50. The answer is 50% and not 99%, only 50%. You may ask why. Because the disease is rare. Let us think about 10,000 people. 100 people have the disease. Of these, 99 tests are positive. 9,900 people do not have the disease. And of these, 1%, which is 99 people, have a test positive by mistake. So there are 198 positive tests total, and only 99 are true positives. 99 out of 100, 98 equals exactly 1/2. This is why doctors do follow-up tests, and this is why understanding Bayes' theorem matters in real life.